Hello, this is Omprakash Yadav. Uh, Today I am going to start acceleration analysis of the mechanism. I have completed the velocity analysis of the mechanism. Now going to start the acceleration analysis of mechanism. So let us see some basic things. Then I will see that acceleration diagram or acceleration analysis for a link. Then I will move for a mechanism. So let us start from a basic. So first thing is that type of acceleration associated with a link or body. Suppose there is a body or there is a link that is moving. So how many number of or which kind of acceleration are associated with that link or that body? So if any link, if the velocity of any link or body, if the velocity of any link or body is changing with time in magnitude and the direction both, that is what the velocity of any body or link is changing in magnitude and the direction both, then that body or link will be subjected to two kind of acceleration. What are the two kind of acceleration? Tangential acceleration and radial acceleration. Tangential acceleration and centripetal or radial acceleration. Radial acceleration. So two kind of acceleration are associated. To discuss and derive the expression, let us take a link AOA. Let us take a link OA. So this link OA is rotating about this O and this end is A. The trace of point A is a circle. Suppose length of link OA is R. At any time t, its angular velocity is omega, and this is associated with a angular acceleration alpha. Means omega keep on changing. So in a small time, that is t plus del t, after the time t plus del t, that means what? At a time t, then after the time del t, means at a time t plus del t, this link OA is moved to the position OA dash. Say this angle is del theta, so that has moved in a small time. This del t in a small time del t, they have moved an angle of del theta. So its length is r, its angular velocity at that time is omega. So velocity of point A. First thing is that velocity of point A with respect to O will be perpendicular to OA. So that is in this direction. And apply the formula V barabar r omega. Its radius r into its angular velocity at that time is omega. So now next position is A dash. Its velocity again will be perpendicular to the link OA. So VA dash will be again r into angular velocity of that link at that time. Let us see what will be the angular velocity of that link OA dash at that time. If the angular acceleration is alpha, then net angular velocity will be omega plus delta omega. Omega plus delta omega. So how to get this delta omega? Chunki alpha is equal to delta omega beta ki del t. So from here I am getting del omega is equal to alpha into del t. So what will be omega plus del omega is equal to this omega plus alpha into del t. So this omega plus alpha into del t will be the angular velocity of this link OA dash at the time t plus del t. So what will be its velocity of point A dash VA dash? R into its angular velocity omega into alpha into del omega plus alpha into del t. So you know the velocity of point A, you know the velocity of point A dash. Velocity of point A dash. Okay. Now let us see one by one. So let us see first tangential acceleration. I am denoting this by AT. Here I will write something more, so I am writing this T here. So tangential acceleration AT. Suppose this is the x direction and this is the y direction. So along the x direction I am taking the change. So first let us define what is the tangential acceleration. So acceleration due to change of magnitude of the velocity. What is the tangential acceleration? Or it is the acceleration due to change of magnitude of velocity. Magnitude of velocity. So this is not due to the change of direction of the velocity vector. This is due to the change of magnitude of velocity vector. So tangential acceleration is an acceleration which is associated due to change of magnitude of the velocity vector only. Due to the change in magnitude of the velocity vector, which can be calculated as its direction is perpendicular to the length. So tangential acceleration is equal to change in velocity perpendicular to length OA, that is in this direction, divided by time del t. So let us see that what is change in velocity perpendicular to OA in this direction, final minus initial. So this is VA dash, that angle will be del theta, so it's a component. This can be resolved into two components, one along the x-axis and another along the y-axis. So this angle will be again, if this angle is del theta, that angle will be del theta. So its component will be VA dash cos del theta, and this component will be VA dash sin del theta. VA dash sin del theta. So final along this direction, so this is this one. So VA dash cos del theta minus VA divided by time del t. Let us put the value of VA dash from here. Look at this is what R omega plus alpha into del t into cos del theta minus VA is equal to R omega divided by del t. Let us open this. So this becomes R omega plus R alpha into del t. This cos del theta, when the time is very small, means what? Del t is tending to 0. When I am taking the limit, del t is tending to 0, then this del theta is also tending to 0. Then you will find that this cos del theta is tending to 1. Then this cos del theta will be tending to 1. That is 1 minus R omega divided by this del t. So R omega has gone. So what I am getting? This alpha into R, and this del t has gone. So what I have get from here? So this 80 so this has gone, this del t has gone, so I am getting 80 is equal to R alpha. So tangential acceleration 80 is equal to R alpha. Tangential acceleration 80 is equal to radius into angular acceleration of the link. Now you see, this is the magnitude. Okay, same thing can be written in that way. So this R and this alpha is equal to d omega. This d omega divided by dt. This R is constant, okay, so can be taken inside to this differentiation. So same thing can be written as d by dt R omega. You know that V is equal to R omega. So I am getting dV by dt. So conclusion is that tangential acceleration is equal to dV by dt is equal to R alpha. So tangential acceleration is given by 80 is equal to dV by dt is equal to R into alpha. Let us see its direction. Look at here. So this is the link OA. Velocity of point A with respect to wave will be perpendicular to link OA. So this is the velocity of point A with respect to O, that is fixed, absolute. So what will be direction of 80? That will be perpendicular to link OA. That is clear that tangential acceleration will be perpendicular to the link, but that will be along the velocity vector or opposite to the velocity vector. This depend upon the link is accelerating or retarding. So for the acceleration, 80 will be along the velocity vector, but for retardation 80 will be opposite to the velocity vector, perpendicular to link OA, that is fixed. So for the acceleration of the link AT will be along the velocity vector, but for retardation of the link OA, AT will be just opposite to the velocity vector. So direction of AT is also clear. So direction of AT is always perpendicular to the link, but along the velocity vector for the acceleration and opposite to the velocity vector for the retardation. Okay, very clear. Now, suppose that link is moving with a constant angular velocity omega. If this link will move with a constant angular velocity omega, so look at here, omega is a constant. Then this d omega upon dt, its the differentiation will be 0, which is what? Alpha. That is angular acceleration will be 0, alpha will be 0. So this tangential acceleration will be 0. Means if the link OA is rotating with the constant angular velocity with the uniform angular velocity omega, then its a tangential acceleration will be 0. Okay, when the omega is constant, tangential acceleration will be 0. Clear? That is known as the uniform angular velocity motion. Motion with the uniform angular velocity. Now, let us see the another component. So that is what the radial acceleration, radial or centripetal. Radial or centripetal acceleration, this is denoted by AR. This is denoted by what? AR. AR. So what is the radial acceleration? First let us see what is the radial acceleration or centripetal acceleration. It is the acceleration due to change of direction of the velocity vector. So this is because of what? Because of change in direction of the velocity vector. So what is the radial acceleration? It is the acceleration due to change of direction of the velocity vector. So velocity vector, that is no, its direction is always towards the center of rotation. So that link is rotating about this O. So always its direction will be from A to O. From A to O. Radial acceleration is always toward the center. Always toward the center of rotation. So this can be get as change in velocity parallel to link OA divided by the time del t, divided by the time del t, divided by the time del t. Then from this formula you can get change in velocity parallel to OA bata ke del t. So whole, what is the final component of parallel to OA? That is VA dash sin theta. So this is what VA dash sin del theta minus, this is having component only in x direction, not in y direction. So that will be 0 divided by this del t, divided by del t. When del t is, when I am taking the limit del t is tending to 0, then this del theta is tending to what? When del t is tending to 0, then this sin del theta is tending to del theta. Well, theta is very small, sin theta is equal to theta, cos theta is equal to 1. So same thing I am using. So in the limit, this sin del theta becomes what? Del theta. So this VA dash into del theta divided by what? Del t. Take the limit. So limit del t is tending to 0, VA dash. So VA dash is equal to R omega plus alpha into del t into del theta. This divided by what? Del t. So AT, sorry, this is not AT, this is the radial acceleration. This is the radial acceleration. So limit del t is tending to 0, R omega plus alpha del t del theta divided by del t. So this limit del t is tending to 0. What I am getting? Let us multiply. So I am getting R omega into del theta plus R into alpha into del t into del theta divided by del t. Look at here. this is the product of two small quantity del t and del theta, so can be neglected, means you take 0, can be neglected. So what you are getting, limit of del t is tending to 0, this r omega del theta divided by del t, or this r omega in the limit del theta upon del t can be written as d theta divided by dt. This is from the first differentiation, and you know that what is this d theta bata k dt? This is the angular velocity omega at any time. So omega and omega, omega is square. So I am getting r omega square. So radial acceleration AR is equal to r omega square. So radial acceleration AR is equal to r omega square. Okay, I am writing here. So radial acceleration AR is equal to r omega square. And why? What I know that v is equal to r omega. So from here, omega is equal to v divided by r. Let us put it here. So v bata k r ka square, that is r v square bata k r square. So what we are getting, v square divided by r. So radial acceleration AR is equal to v square by r is equal to r omega square. So radial acceleration of the link is given by v square by r is equal to r omega square. V square by r is equal to r omega square. What is its direction? Always toward the center of rotation, that is from A to O, from A to O. So this is the magnitude, and its direction is always from towards the center of rotation, always towards the center of rotation, towards the center of rotation. Now if you know the tangential component, if you know the radial component, then how to get the total acceleration, yeah, final acceleration, final acceleration if the direction of velocity vector is not changing, that is if the particle or link is moving in a linear motion. So when a body or link is moving in a linear motion like a slider, then the direction of velocity vector is not changing. If the direction of velocity vector will not change, then the radial acceleration will be 0. Okay, so this radial is because of changing what, the direction of velocity vector. If the direction of velocity vector is not changing, then the radial acceleration will be 0. Okay, let us here. So this two acceleration. So this is O, this is A. So what you are looking at, tangential acceleration is along this, either this way along this or along this, depending upon acceleration or retardation. And the radial acceleration is always toward the center. So this is one acceleration, this is another acceleration. So its resultant will be in between this. So how to get resultant or total acceleration of length, that is what A. So these both are at 90 degree, so can be calculated from this formula, AR ka square plus AT ka square. So net acceleration, resultant या final total acceleration A is equal to under root AR square plus AT square. So this is the from the analytical. Also you can get graphically. So this tangential acceleration is along this. So in magnitude and direction you draw along this direction, that is AT. This is the tail of this vector. This is head of this vector. From the head draw the another vector. That is what the radial acceleration AR. Now you join the tail of first vector to the head of last vector to get the total acceleration. So this is tangential, radial. Then you draw from tail of the first vector to the head of the last vector to get the resultant acceleration. Also this angle can be measured, that at what angle from AT is the final or total acceleration. Okay, So these are the two accelerations. So you know what are the magnitude, what are its direction, in what condition, that will be 0. So I have discussed this much thing. Now I am going to start the acceleration of a link. Now going to personalize and going to enter into the core things, that is the acceleration of a link. This is the general. Now acceleration diagram of a link. Acceleration diagram of link. Acceleration diagram of link. Suppose this is any link AB. Suppose this is any link AB which is rotating with an angular velocity omega, and that is associated with also a angular acceleration alpha. Okay, so this is any link AB which is rotating at any time. This is rotating with an angular velocity omega, which is associated with angular acceleration alpha, that is omega is changing with time. Let's see, जब आप A पे बैठ के B पे देखेंगे, then what you will see that velocity of point B with respect to A will be perpendicular to AB. Will be what? Perpendicular to AB. So this is the velocity of point B with respect to A, that will be what? Perpendicular to AB and in the direction of rotation. So this is the velocity of point B with respect to A in magnitude and the direction. Now, what will be the direction of radial acceleration? So radial acceleration, you know that is always toward the center of rotation. So radial acceleration of point B with respect to A. So what will be its direction? Always toward the center of rotation. Now, another thing is the tangential acceleration. So tangential acceleration is perpendicular to the link AB and along the direction of velocity for the acceleration and opposite to the direction of velocity for the retardation. Let us take the acceleration. So AT will be along the direction of velocity perpendicular to this AB. So this tangential acceleration will be along this direction of B with respect to A. So tangential acceleration of B with respect to A. This is the radial acceleration of B with respect to A. This is what ATBA, tangential acceleration of B with respect to A, or B with respect to A. So this link is subjected to the two acceleration because of magnitude and direction both are changing for the link AB for the velocity. So this is the acceleration associated with a link. So I have given the personal name to each and everything. Now let us draw its acceleration diagram. Let us assume that point. One thing more. Any capital letter in the space diagram is represented by small letter, corresponding small letter in the velocity diagram, and in acceleration diagram, a small letter with dash will be presented. A small letter with dash. So let us assume that acceleration of point B is here. Suppose let us assume that acceleration of point B is here. Now let us see that this link is subjected to two accelerations. So by the vector method you have to find out its total acceleration. So look at here, radial is along from B to A. So draw a line parallel to AB from B to A by dot line. By what? Dot line. By dot line. So this is what the ARBA, radial acceleration of B with respect to A, that is from B to A. So draw a line parallel to BA. Now you know that with both the acceleration are at 90 degree. Now you draw the tangential acceleration. Its direction is here from the tail of this head of this vector. Let us draw the another at 90 degree, that is along this. Draw the another. So this is what the This is what the tangential acceleration of B with respect to A. With respect to A, say this is yours. So final acceleration will be drawn by the complete line, and radial acceleration and tangential acceleration will be drawn by the dot line. Now you join this tail of the first vector to the head of the last vector by this complete line. So this will be the resultant acceleration of B with respect to A. So this is the total or resultant acceleration of B with respect to A. So this is the acceleration diagram for a link. Now let us use the previous formula and derive the expression for the same. So you know that the tangential acceleration AT is equal to R into alpha. So what will be AT of B with respect to A? Radius will be AB. Radius will be AB into alpha of the length AB. Let us say this is what alpha AB, alpha B, that are the same thing. That is for a length. That is for a length. So alpha BA or alpha AB also you can write. So AT BA is equal to what? AB into alpha BA. So you are having one relation from here. So this is the personal relation for a link. So what you are having the another relation, radial acceleration R is equal to V square bata K, R is equal to R omega square. So AR of B with respect to A is equal to what? Velocity of point B with respect to A ka square. Only you take the magnitude divided by radius of the link. Let us say this is AB. And another formula R, that is what? AB, length of the link AB, into omega of B with respect to A chi square. So this omega also can be written as angular velocity of B with respect to angular velocity of link AB. You say that will better, you say the angular velocity of link AB or B. That is omega B, or you can write simply omega. Okay, so this is the another formula for the radial acceleration of the length, and the total acceleration can be calculated from this formula, because these both are at the 90 degree. So A R B chi square plus AT B ka square. These both are at 90 degree. So by this you can calculate the resultant acceleration. So radial acceleration of B with respect to A chi square plus tangential acceleration of B with respect to A chi square. So that will be the resultant acceleration, and its direction and the magnitude also you can get from here. Okay, so this fundamental I will use to draw the complete acceleration diagram for the mechanism. In the next lecture I will see for the mechanism. Before solving the numerical, I will give the step how to move step by step, one by one. Okay, thank you very much.